Hello class, in this video we are going to cover section 3.7, arguments and truth tables. Excuse me. So what is an argument in logic? An argument consists of a bunch of statements, and the structure of the statements has two parts. The first part is called the premises. An argument could have only one premise or more than one premises. And the second part of an argument is a conclusion. So the standard form of an argument in logic is given like this: premise 1, the second line premise 2, and you draw a horizontal line to separate premises and conclusion. The horizontal line separates the two parts in an argument. Sometimes we have this notation or symbol. Sometimes we don't even have that notation. This means therefore. Some books don't even use this notation, only use the horizontal line to separate the two parts. You will not have any confusion without the notation. Okay, yeah. An argument has two parts: the given statements called the premises and a conclusion. The general form is like this. Between the two parts, premises and conclusion, we use a horizontal bar to separate them. How do we judge or evaluate an argument? We use validity to evaluate an argument. An argument is valid if the conclusion is true whenever the premises are true. In other words, an argument is valid if the conclusion can be derived directly from the premises. Logically, those premises would directly give you the conclusion. The conclusion can be drawn directly from the premises. Then the argument is valid. Otherwise, the argument is invalid. An invalid argument is also called a fallacy. So those are very basic concepts that we need to remember, understand and remember. How do we know if a given argument valid or invalid? How do we determine the validity? We can use truth tables. Truth tables we learned from yesterday can be used as the tool to test the validity of an argument. Let's see how does the truth table work to test the validity of an argument. We have the following steps to test the validity of an argument with a truth table. Firstly, use a letter to represent each simple statement in the argument. Secondly, express the premises and the conclusion symbolically. Thirdly, write a symbolic conditional statement of the form. As you can see, an argument is a conditional compound statement, conditional. The antecedent of the conditional statement are the conjunction, is the conjunction of all those premises. The conclusion of the conditional, of course, is just the conclusion in the argument. And here is the number of premises in the first part. Number 4. Step 4. Construct a truth table for the conditional statement in step 3. Step 5. If the final column of the truth table has all truths. In other words, if the truth table helps us to determine the compound statement, the conditional compound statement that is equivalent to the given argument is a tautology. Tautology is a statement always true in all cases, then the given argument is valid. Otherwise, it's invalid. Okay, so those steps gives us the process of using truth table to test the validity of an argument. Also explain why. Yeah, especially step 3. Step 3 gives you the reason. How do we see an argument as a compound statement? Yeah, it's actually a conditional compound statement. The antecedent is the conjunction of all the premises. The conclusion is just a conclusion. Okay, let's use the truth table to determine the validity of a given argument. Let's look at this example. Use a truth table to determine whether the symbolic form of the argument is valid or invalid. Okay, so you see the horizontal bar, right? You are going to translate the horizontal bar as the conditional logical connective. Yeah. And the antecedent is the conjunction of all the given premises. How many premises do we have? We have 2 premises, right? This is the first one, the second one. Yeah. So the first component of the conjunction is not P or Q. That's the first component, first premise. Conjunct with the second premise, P. Yeah, together, that conjunction is the antecedent of the conditional that represents the given argument. And what is the conclusion? Conclusion is just a Q, right? Yeah. Sometimes I feel like this notation really not very necessary. So this conditional statement is equivalent to the given argument. Yeah. If premise 1 and premise 2, then we have the conclusion. Right? Yeah, same with the argument. You're arguing. Yeah. Let's see, how do we construct the truth table? Since this conditional statement involves 2 simple statements, the first 2 columns in the table start from P and Q, follow with the 4 cases. Do you remember the 4 cases? Truth, 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 false, false, truth, false, false, right? Case number 1, case number 2, case number 3, case number 4. And the last column, I'm going to have my target statement is the conditional I have here. So the antecedent is a conjunction, not P or Q, and P. By the way, this parenthesis is necessary, otherwise you will have confusion. Implies Q. This is our target statement. Okay, it is conditional. It has 2 parts, antecedent and conclusion. All right? Yeah. So I'm going to have one more column here. You might think it's unnecessary, but I like this way. So this is the conclusion. All right? And my let me see if I can change this here. Yeah, move this over to the left. Yeah, so I can have two columns here. This is conclusion. And the antecedent is a conjunction. not P or Q, and P. All right, yeah. So I split this column as 2. This is the antecedent, this is the conclusion, just for my convenience. And this is antecedent, this is the conclusion. The antecedent is pretty complicated. One component is not P or Q. Not P or Q. The other component is P, is right here. And we also need a not P here. Okay, so that should be enough. Let me label them. This is number 1, 2, 3, 4, 5, 6, 7. I have 1, 2, 3, 4, 5, 6, 7 columns in my truth table. Column 3 is not P. We are going to have the opposite truth values from column 1. So when P is T, not P is F. When P is T, not P is F. When P is F, not P is T. When P is F, not P is T. Yeah. So column 1 and column 3 should have opposite truth values. Okay. And then column 4. Column 4 is a disjunction. Column 4 is disjunction of column 3 and column 2. Yeah, the 2 columns preceding column 4. For a disjunction to be false, both of them need to be false. We learned this 2 days ago, right? For a disjunction to be false, both of the 2 component statements need to be false. So only the second case, the disjunction is false. In all other cases, the disjunction is true, true, true. Now let's take care of column 5. Column 5 is a conjunction. It is column 4 and column 1, or column 1 conjunct with column 4. The order really doesn't matter. Yeah. So in disjunction and conjunction, the 2 component, the order of the 2 component statements doesn't matter. But conditional, it matters. Conditional, you cannot just randomly switch the antecedent and conclusion. So column 5 is column 1 and column 4 for the conjunction. Okay, this is column 1, this is column 4. Yeah, we are taking conjunction. For a conjunction to be true, both of them have to be true and false, false, false. For a conjunction to be true, both of them have to be true. And then our other 3 cases are false, false, false. Okay, column 6. Yeah, you might think column 6 is same with column 2, right? Yeah, it is the same, but just for convenience, later when I do the column 7, so just copy Q, copy column 2 to column 6, TF, TF. All right, now we are ready for column 7. Column 7 is if column 5, then column 6. So the antecedent is column 5, conclusion is column 6. So we are looking for trusted friend forever, right? Trusted friends forever. We don't have. That means what? They are all T, temporary. We don't have any case in which the antecedent is true and the consequence is false. So the conditional is not possible to be false. In all 4 cases, the conditional is true. So this is a tautology. This is tautology. Okay. not P or Q. Now P occurs, not P or Q. So Q, yeah. So we use the truth table to determine this argument is valid. Now we can answer the question. The argument is valid. All right, this is the process of using truth table to determine or test the validity of a given argument. Let's continue. Translate the argument into symbolic form, then determine whether the argument is valid or invalid. Okay, so two premises. This is number one, this is number two. Number one, you must eat well or you will not be healthy. Number two, I eat well. Conclusion, I am healthy. I think what we need to ignore, not just the tense, past, present, or future tense. We also need to ignore the subjective, you or I. Yeah, let's make it simple. Let's say P is eat well. Q is healthy. Yeah, healthy. All right. So how do we use a symbolic format to represent this argument? You must eat well. You must eat well. P or, so it's a disjunction. You will not be healthy, not Q. That's the first premises. And second premise, you eat well. You eat well, P. And conclusion. Do we have the conclusion that healthy? You are healthy, Q. So that's the translation of this argument. This argument can be written or expressed by using this conditional statement. And let's use the table. Let's use the table to determine tests. I wanted the whole thing here. I'll just write it again. So the symbolic format is P or not Q, and P implies Q. So that's the compound statement. Yeah, we have the table given. There's so many big space. Let me get rid of the space here. No, it doesn't work. Okay, so let's see. The conditional statement involves two simple statements. So the first two columns are P and Q, and with four cases: T, 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 F, F, T, F, F. This is case 1, case 2, case 3, case 4. All right. The last column is going to be the conditional. P or not Q, and P implies Q. And it has two pieces. I'm going to do the same thing. Q is the conclusion. P or not Q and P. P or not Q and P. That's the antecedent. P or not Q, and P, that's antecedent. And the antecedent is a conjunction. One of the P's is P or not Q. So obviously we need to know what is not Q, right? This is pretty similar with the previous example. It's different, of course it's different. Yeah, let's see. This is column 1, 2, 3, 4, 5, 6, and 7. Column 1 and column 2 and column 3. Those two columns need to have the opposite values. So TF, FT, TF, FT. Yeah, make sure the two columns have opposite truth values. Column 4. Column 4 is a disjunction. Column 4 is column 1 or column 3. Column 4 is column 1 or column 3. 1 or 3. So for the disjunction to be false, both of them need to be false. For the disjunction to be false, both of them need to be false. So only in case 3, we have the disjunction as false. All other 3 cases, we have true. And that's column 4. Column 5 is a conjunction. It is column 1 and column 4. Yeah, so column 5 is column 1 and column 4. Well, column 4 and column 1, the order doesn't matter, as I mentioned earlier. So for a conjunction, so we are looking at, I don't mind to color this. Yeah. So we are doing the conjunction here. Those two yellow columns, we need to do the conjunction. Only when both of them are true, we have true. For a conjunction to be true, both of the two components need to be true. And the other two cases, the conjunction is false. Okay, now we copy. Let me erase the color. Now we copy column 2 to column 6. So we have TF, TF. Now we are ready for column 7. Column 7 is column 5 implies column 6. If column 5, then column 6 is conditional. So we are looking for, let me this time color, this is antecedent, this is conclusion. We are looking for trusted friends forever, right? Do we have a trusted friends forever? Yes, we do. Yeah, only one. In case 2, we have a trusted friends forever. And all other 3 cases, we have temporary, temporary, temporary. So what do you think? What's your conclusion about the given argument? Valid or invalid? Invalid, okay? Yeah, because the last column is not all true. To use the truth table to test the validity of an argument, we have to look at the last column after we finish the table. Only when the last column, in all cases, the last column are true, we say the argument is valid. Otherwise it's invalid, even we only have 1 false here. Okay, let's continue. This table is very important, okay? Yeah, the standard forms of arguments. It gives us a few valid arguments based on reasonings. Also, some fallacies based on common mistake by misusing the reasonings. So I'm going to prove the table right here. Okay. Yeah. I have more space here. So number one is direct reasoning. Direct reasoning has two premises. If P implies Q and P, then we have Q. Yeah, we are going to use the truth table to test the validity of this argument. And this argument is called direct reasoning. If you think about, the first premise tells us P implies Q. If P, then Q. And now we also know P occurs. Then do we have directly? Do we have Q occur directly? Yeah, that is very straightforward, right? Direct reasoning. As an argument, yeah. So we are going to, as a practice, we are going to use the truth table to prove the validity of this direct reasoning. So we are going to translate the first. Yeah, translate the first. P implies Q and, and P implies Q. So that's the translation of the argument. And we are going to use the truth table to test the validity of the conditional here. Okay. The conditional statement involves two simple statements. 2, 3, 4. Okay. So this is P, this is Q. We have TT, TF, FT, FF. And as I mentioned, I like to start from the last column. Yeah, you should do this on your scratch paper. The last column is the target statement. P implies Q, and P implies Q. All right? Yeah, so I'm going to have the antecedent and conclusion preceding my target conditional compound statement. So conclusion is Q. Antecedent is a conjunction. P implies Q. We have to have this parenthesis, very important, because of the level of dominance. So yeah, let me double check. That is the antecedent. This is the conclusion. Okay. Antecedent is complicated. Yeah, it's compound. We need look at both of the two components. The first component is P implies Q. The second component is P. Yeah, P implies Q and P. All right, so we are ready. Let's do P implies Q. For the conditional to be true, for the conditional to be false, we need a antecedent as true, but consequence is false, right? So trust friends forever. This is case 1, case 2, case 3, case 4. Only in case 2, the conditional in column 3. And this is column 1, column 2, column 3, column 4, 5, 6, 7. Yeah. The conditional in column 3 is false in case 2. All other 3 cases, they are true. Okay. So column 4 is the same with column 1, so we just copy TTFF. And column 5 is the conjunction of column 3 and column 4. So for the conjunction to be true, both of them need to be true. So TF, F, F. For the conjunction to be true, both of the two components, 3 and 4, need to be true. And that's column 5. Column 6 is the same with column 2. Let's just copy it. TF, TF. Yeah, that's what I would do. You don't have to do that, but I just think this way is more convenient. Put the two components next to each other. And now we are ready for number 7. Column 7 is a conditional with column 5 as antecedent, column 6 as conclusion. So you see, this is more convenient, right? So we are looking for trusted friends forever. We don't have. Yeah, we don't have any case in which column 5 is true, but column 6 is false. So that make the last column all true. So this is tautology. Yeah, it is valid. So we just proved this is valid. Yeah, the first one, it is the direct reasoning. Yeah, you need to remember, we need to make effort to remember those simple things. It is a direct reasoning. If P implies Q, and now P occurs, now of course we have Q because P directly leads to Q, right? Yeah, directly result in Q. That's the first one. Second one, contrapositive reasoning. Let me copy that. Let's see if I can copy the table here one more time. Yeah. This time we are going to prove the contrapositive reasoning. And what is contrapositive? Yeah, let me briefly introduce some concepts. Converse, inverse, contrapositive, okay? So if we have P implies Q, then the converse of this statement, the compound statement or conditional statement, is Q implies P. The inverse of the conditional, yeah, the given, this is the given, P implies Q, would it be not P implies not Q. And the contrapositive of the given conditional is not Q implies not P. All right, not Q implies not P. So this is, let's say, given, yeah, given statement. So very important is the given statement P implies Q and is a contrapositive, not P implies not Q, are equivalent. Okay, equivalent means either both true or both false. Yeah. And another thing you want to know is the converse and the inverse, they are equivalent. Why? Look at the two oranges. They are actually, the two oranges actually are contrapositive of each other. Okay? But if the given statement is true, the converse not necessary to be true. The inverse not necessary to be true. But its contrapositive definitely is true. Okay? Okay, so let's give an example quickly. Let's say P is it's raining. Q is the grass is wet. All right? Yeah. So the given statement is if it's raining, then the grass is wet. Let's say the grass is outdoor. Of course, if it's raining, the grass is gonna get wet, right? So this is true. Yeah. Suppose in this example, then its converse would be if the grass is wet, then it's raining. That not necessarily, right? Yeah. The grass is wet could be from any other reasons. Maybe you just pour a bottle of water on top of the grass. Doesn't mean it's raining, right? Yeah. The inverse would be if it's not raining, then the grass is not wet. That's not always true either. Yeah. If it's not raining, the grass definitely is not wet. It's possible it's wet. Yeah. Even it's not raining, you can hose it, right? You can put the water manually. Yeah, it doesn't have to be from the sky. Yeah, but the contrapositive, let's see, what's the contrapositive of the given statement? If the grass is not wet, then it's not raining. It is true. Yeah, if the grass is dry, not wet, then you look out. The grass is dry, not wet. That means not raining, right? Because if it's raining, the grass is gonna get wet. Does that make sense? Yeah. This is just one example. You can find any other example. The point here is you need to remember, if you have a given conditional statement, the definition of its converse, the definition of its inverse, the definition of its counterpositive. Also, you need to remember, the given conditional and its counterpositive are equivalent, either both true or both false. And its converse and inverse are equivalent, either both true or both false. Yeah. If the given conditional is true, we cannot guarantee its converse is true. We cannot guarantee the inverse is true either. Yeah, just give you the example here. All right. Yeah, we are going to prove the counterpositive reasoning. Let me copy the counterpositive reasoning. P implies Q. P implies Q, not Q. Then we have P implies Q, not Q. Then we have not P. Okay, so that's the counterpositive reasoning. Let's translate to the equivalent conditional statement and use truth table to test its validity. Okay, so let's continue here. P implies Q. First premise. And is upside down B. And not Q implies not P. Okay? Truth table. The truth table gonna have 4 cases only because the conditional only involves 2 simple statements. So P, Q, T, T, TF, F, T, F, F. Case 1, case 2, case 3, case 4. Okay, the last column is going to be our target. Let me write it smaller. P implies Q and not Q implies not P. And I'm going to, my habit, I want the antecedent and the conclusion preceding the conditional. So this is going to be the not P, and this is going to be P implies Q and not Q, not Q. So this is the antecedent, this is the conclusion, and it gives us the last column is the target conditional statement representing the argument. And for the antecedent, we have 2 pieces. This is not Q. The other piece is P implies Q. Sometimes you will see I could have leave more space there, right? Yeah. So the more you practice on the scratch paper, you plan, then you can have a better table than mine. Yeah. Okay, so this is column 1, 2, 3, 4, 5, 6, and 7. Let's get started. Column 3 is P implies Q, with P antecedent, Q conclusion. So we are looking for trust friends forever. Yeah, only the second case give us a false. All other true, true, true. Okay, so that's column 3, very basic. Column 4 is the opposite, is the negation. Column 4 is the negation of column 2, so make sure that you have the value flipped. Yeah, column 2 and column 4 have opposite values. Okay, and column 5 is the conjunction. Column 5, sorry, let me rewrite it. Column 5 is the conjunction of the two columns preceding it. Okay? Yeah, column 5 is column 3 and column 4. Okay, it's a conjunction. For that conjunction to be true, both of them needs to be true. Only the last case. All other cases for false, false, false. And column 6 is the opposite of column 1. So F, F, T, T. Make sure column 1 and column 6 have opposite values. Okay. And column 7 is column 5 implies column 6, with antecedent column 5 and conclusion column 6. Again, we are looking for trusted friends forever. We don't have. We don't have means what? Yeah, let me highlight. This is the antecedent. This is the conclusion. Yeah, we are looking for the case in which the yellow is true, the orange is false. We don't have that. So for all cases, the conditional column 7 is true. So this is a tautology. This is valid. Yeah, we just proved that contrapositive reasoning is valid. Of course, yeah, think about, because I just explained what is a contrapositive, right? If P implies Q, is a contrapositive is not Q, then not P. So P implies Q, and now not Q, of course you have not P. Yeah, if it's raining, then the grass is wet. Now the grass is not wet, and you know it's not raining. Contrapositive reasoning, okay? Number 3, we are going to talk about the disjunctive. Let me copy the table again. It's going to become consuming to prove all those standard form of the arguments, but it's worth it. Okay, disjunctive reasoning has 2. I'm going to only do one of that. Okay, I'm only going to prove this one. Disjunctive number 3. Disjunctive reasoning. Yeah. So the disjunctive reasoning is P or Q and not P. Therefore, Q. Yeah, let's make sense of it. Why is it disjunctive reasoning? Let's say P or Q. Now not P, then definitely Q. So let's say you are dating A and B. This year you are going to marry either A or B, or both. Okay, not good example. Let's say this. Let's say you go to a restaurant that you order a special meal, and the restaurant will give you either. Let me see. How about this? On Saturday, you plan to visit your friend and do house chores. Yeah, your plan for Saturday is visit your friend or doing the house chores. And now you did not visit your friend. It means you're doing your house chores, right? Yeah. Either P or Q or both. But now P doesn't occur, of course Q would occur. Yeah, just feel the reasoning. Translate. We're going to translate this as a conditional. P or Q conjunct with not P implies Q. Truth table. One, 2, 3, 4. Oh, this is too narrow. 4. Okay, so we have case 1, case 2, case 3, case 4. This is column 1, column 2, PQ. T, 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 F, F, T, F, F. Okay, so the last column, as my habit always, is my target. It's my target, so not P. We can have more space here. So P or Q and not P implies Q. And we are going to have the conclusion as here and antecedent here. P or Q and not P. And this antecedent has two pieces. Conjunct is a conjunction with two pieces. First piece is a disjunction. Second piece is not P. Okay, so column 3, column 4, column 5, column 6, column 7. And that's the structure of this truth table. Let's fill in those blanks. For a disjunction to be false, both components need to be false. All other are true. At least the one true would make the disjunction to be true. And column 4 supposed to be the negation. Yeah, column 4 is the negation of column 1, so we're gonna revert, take the opposite of the values. So TF, FF, TT. Yeah, make sure double check number 1, column 1 and column 4. They have opposite values. Okay, so column 5 is the conjunction of column 3 and column 4. Column 5 is a conjunction of column 3 and column 4. For a conjunction to be true, both of them need to be true. Then all other cases is false. Q, the conclusion, column 6 is the same with column 2, so we just need a copy. TF, TF. And column 7 is column 5 implies column 6. Trust the friends forever. Trust friends forever. We don't have. Okay, yeah, one more time. This yellow column is the antecedent. This orange column is the conclusion. There's no case in which the yellow is true, but the conclusion is false. So we have the last column all true. So we proved this is a tautology. The disjunctive reasoning is valid. Transitive reasoning. I'm not going to prove that because it's very time consuming. Let's just try to make sense of it, okay? If P implies Q and Q implies R, then you should have P implies R. Does not make perfect sense. P occur, result in Q. Q occur, result in P, like a domino. So of course, if P occurs, then you eventually will have R occur. And this part is just the contrapositive of P implies R. Yeah, not R implies not P. Yeah, so it's very time consuming. Also, it's gonna have 8 cases because it involves 3 simple statements. Yeah, but its transitive reasoning is very obvious. Very obvious. Okay, let's see the second row in this table. Fallacy. Let me copy the table here. Let's prove the fallacy of a converse. So fallacy of the converse. I just gave you an example to prove that, right? P is raining. Q is the grass outdoor got wet. Now the grass got wet. Can we say it's just raining? Not necessary, right? Yeah, maybe it's not raining. Maybe you just water the grass. Let's prove it. Let's translate it first. P implies Q, and Q gives us the conclusion P. One, two, three, 4. This is P, this is Q, column 1, column 2. T, 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 F, F, T, F, F. The last column is going to be the target. The target is a conditional. P implies Q, and Q gives us P. So I'm going to use this as the conclusion, and this is the antecedent. And it has 2 pieces. Second piece is Q. First piece is conditional. So my table has 5, it is antecedent, 6, 7 column. Column 3, P implies Q. Trust friends forever. Yeah, we have done this tons of times, right? Many times. You should be very familiar with the basic. And the complicated one just consists of a few basics. So only in case this is case 1, case 2, case 3, case 4. Only in case 2 we have true antecedent, false consequent. So that makes column 3 false. And all other cases are true. Column 4 is the same with column 2. So T, F, T, F. Column 5 is the conjunction of 3 and 4. Column 5 is conjunction of 3 and 4. So for the conjunction to be true, both of them need to be true. So we have T here, and then the other 2 cases we have false. And then copy column 1 to column 6. T, T, F, F. And column 7 has antecedent 5, conclusion 6. Yeah, so the antecedent is yellow, conclusion is orange. Let's see, do we have any cases in which yellow is true, orange is false? We do, right here, right? Trust the friends forever. And all other cases T, T, T. It doesn't matter, we do not have all true, so this is invalid. This is a fallacy. Okay? We proved the fallacy of converse. So similarly, you can prove the fallacy of inverse. Misuse of disjunctive reasoning and misuse of transitive reasoning. I believe you can understand the rest because we have the first few explained in detail. You can try to prove the other standard form of reasoning in the table. It's very time consuming. Yeah. So if you have any request, like can you prove this fallacy of inverse, you can email me. Then I can send you the video. All right. Yeah. For this class, let's just go back. It's very it's already a very long video, right? Let's see how many minutes now. Okay, so yeah, let's continue the guided notes. Use the standard forms of valid arguments to draw a valid conclusion from the given premises. You exercise or you do not feel energized. I do not exercise, therefore, okay. If we let P be exercise, let the Q be not energized. then the argument here is you exercise or you not energized. Now you do not exercise, therefore you are not energized. So this is disjunctive reasoning, okay? Disjunctive reasoning, the one we just proved right here. If you don't exercise, of course, you are not energized. So therefore, you do not feel energized. Disjunctive reasoning. Yeah, you exercise or not energized. Now you do not exercise, of course, you are not energized. Here I use a negation. The statement of Q is a negation, is negative, not energized. Translate the argument into symbolic form, then determine whether the argument is valid or invalid. You may use a truth table or, if applicable, compare the argument's symbolic form to a standard valid or invalid form. So use the standard format of arguments is a shortcut. You don't have to always prove using the table. If you can prove using the reasoning or misuse of reasoning, fallacy, something like that, is more efficient. Let's see this one. If I'm at the beach, then I swim in the ocean. If I swim in the ocean, then I feel refreshed. So, if I'm not at the beach, then I do not feel refreshed. Symbolic form. I see 3, okay? P is I'm at the beach. Q is I swim in the ocean. R is I feel refreshed. Okay, so we have to use symbols to represent the basic statements in the argument. Okay, so we can write the argument as if P then Q, if Q then R. Oh, hold on. Can we say not if I, yeah, can we say not P implies not R? Yeah, I'm not at the beach. Not P implies not R. This is invalid. This is a fallacy, okay? Why? This is a misuse of the transitive here. P implies Q, Q implies R. Does not give us not P implies not R. This is a misuse of transitive reasoning, okay? You don't have to use the table. It's going to be very time consuming if you use the table, but use the standard. Yeah, there's a table here. If you want, you can try that. All right, that's everything for this video, for this section. It's a very long video. Thank you for watching. I'll see you next time.